Hello guys, welcome to session 2 of your Wi-Fi pen testing bootcamp. Uh, okay. Yes. Mike, that's right. So I have V1 because I have this card for like 4 or 5 years now. But now it is not very easy to find V1, but V2 also works. That's what people have told me. And in my when I look for blogs and resources for V2, everyone is saying that for our purpose it is working well. Uh, so you can actually use it if you can find V1. You can use that then. But I was not able to find a reliable link which can uh, ship the V1 for us. So that's why I have posted this one. So guys, just so that I know that you guys can hear me clearly, please drop a hi or hello in the live instructor interaction channel. Yeah, okay. Okay, great. Yeah, so I am audible. Uh, okay. So before we start, last time in the session 1, so we had given some assignments. There were two parts of the assignments. First one was the lab assignment, in which you have to do all of these labs that I have mentioned here. I hope you have done these. If you haven't, please try to do these because till the time you don't practice on your own, it will be really difficult to understand all the things and to become very familiar to this. Uh, the second part was some questions that I had given to you, to read about and to find answers for. Uh, First of this question, one of the questions was to figure out how to perform remote sniffing. And what is remote sniffing here? Remote sniffing is the setup when you have one machine with you, you have another machine some other place, and this machine is accessible over the internet or over the network. And what you are doing is on the remote machine, you have attached the Wi-Fi adapter. And now from your local machine, you are pulling the packets that the remote machine is sniffing in its own environment, right? So that is what will qualify as remote sniffing. So there are multiple ways to perform remote sniffing. The easiest way is to use the tools that are already there, that are stable. We just need to install them, right? So that method will use TCP dump, SSH, and Wireshark. So how we are going to do this? First of all, we have to install SSH service on the remote machine because obviously you need some way to communicate with this machine and to get the packets, right? And again, in this case, we are talking about streaming the packets. So you are sending the packets over to the local machine from the remote machine as soon as you are catching them or as soon as you are sniffing them. Right? You don't want to do the batch processing kind of thing, like first you are storing packets in PCAP on the remote machine, and then you are bringing in the PCAP, right? So that is not what we are talking about. We are talking about live traffic analysis, right? So you are streaming the traffic to your machine, and on your machine now you want to analyze this. So first of all, we need to install on the remote machine. Then on the local machine, we need to install Wireshark. And I'm assuming that our local machine is also Linux and our remote machine is also Linux. And then from on our remote machine, we have to make sure that the Wi-Fi card, the Wi-Fi adapter, right? So here we can consider that the interface that we have connected to that machine, it is mounted as WLAN 0. So we will put this WLAN 0 into monitor mode. We will then run aerodump or something which will make this interface hop on different channels, right? So that's the setup that you need on the remote side. From the local machine now, we will use SSH and we will use this command here. So what this command is doing, we are using a root user to SSH into this machine. This is the host name of that machine. You can also use the IP address And after that, we are defining the command that we want to run. So we want to run TCP dump on the remote machine, right? You also have to install the TCP dump. And in with the TCP dump, you are giving these options. So what these options are going to do, they are going to capture the traffic on WLAN 0, and then this traffic will be passed to this pipe, right? So what we are doing here is we are capturing the packets here. These packets will be sent over the SSH connection to the local machine. And on the local machine, we are opening Wireshark. And due to these parameters that we have given here, Wireshark is going to show you these streaming packets in its interface. And when you can see these packets in the Wireshark, obviously then you can deploy your filters. You can then use the analysis techniques to analyze the traffic, right? This is the easy way of doing things. But again, because you're using TCP dump, you're using SSH, Wireshark, so everything will work perfectly because everything is stable, right? You don't have to put in a lot of effort, but it will come with its own limitations, right? For example, suppose if you want to do the same thing with like say 15 machines, right? So think of these machines, right? So replace the machine with a customized access point, right? Which is just doing the sniffing. So now you can have multiple of these devices and you can then fetch the packets. But the problem is if you are going to use this SSH based approach, right? It might not be the best approach to use. And second thing, here you're using Wireshark, right? So again, means Wireshark will have its own limitations. If you are getting a lot of packet volume, right, then your machine will become constrained, right? Your Wireshark will hang and all of those problems. So in those cases, what you can do is, uh, if you want to do this, what you can do is instead of using these inbuilt solutions, you can use a Python script. Uh, you can use a SCAPI, or you can even use the raw sockets, and you can capture the packets on WLAN 0 on the remote machine, right? So Python script is running on the remote machine. And after capturing these packets, what this Python script will do, it will create a IPv4 or IPv6 packet, and it will then pack this Wi-Fi packet into this packet, right? In this IPv4 or IPv6 packet, and then the address, right? The address of this packet that the Python script will create will be of our local machine. So when this script will send this packet will then reach our local machine. But now thing is, if we are doing this, and again, if we want to use Wireshark or something for easy analysis, how we can do this, right? How the Wireshark will know that it's a WLAN packet, right? Because all it will see is some kind of IPv4 or IPv6 packet, which it won't be able to comprehend, right? So in that case, what we can do is we can use something called Aruba ERM standard. So Aruba ERM is a industry standard that is used to transmit these Wi-Fi packets, right? If you have captured the Wi-Fi packets, you want to transmit them over the IPv4, IPv6 networks, you can use Aruba ERM standard. And Wireshark has a Aruba ERM standard on it. It comes, by default. You just have to enable it. So your Wireshark will be able to understand what this packet is. So if you open this link here, it will actually show you the code for the dissector, the Aruba ERM dissector of Wireshark. And in that code, you will actually see that in the comments, the structure for different types of Aruba ERM packet are defined, right? So structures are here. If you use type 0, this is what the structure you have to use. And this is the packet structure. This is the header structure, right? Similarly, for type 1, you have different one. For type 3, you have different one. So all of these structures, all of these packet headers, right, you can create with the Python script. So once you do, and once you send these packets over to the local machine, and suppose you are sending all of these packets on a specific port, say 5555, right? So this is how these packets will look. So here, assume that your remote machine, which can be a Linux machine, it can be a modified router, right? It is using 192.168.1.1, right? That is the IP address of the remote machine. And this is the IP address of our local machine. And as you can observe here, it is saying that it is able to receive packets on port 5555. And this packet looks like UDP packet, right? Now it is not able to understand or interpret it, right? So what we have to do here is we have to go to edit. From there, we will go to preferences. And from there, we have to select the protocols section, right? Once you are there, you have to look for Aruba ERM, and you have to define the port number on which these packets are coming. So because we are using 5555 port, we will define this here. As soon as we press OK, all of these packets will be now interpreted as Aruba ERM. So you can observe, right? Protocol is Aruba ERM, but still it is not showing us what is inside it, right? And for that, we have to decode them. So you just right click on any one of these packets, you select decode as, and from there you actually select the type that you are using. Now you know this type because when you were sending the packets at that time, you have you have selected that specific type, and then you have used your Python script to create that header, right? That is what you are seeing here. So we are selecting type 3 because that's what we are using, right? If you're using type 2, type 1, you can use that. And once you do this, after that, you will see that now Wireshark will start understanding all of these packets, right? So you can observe uh, we have Ethernet frame. Inside that, we have IPv4 packet. And inside that, we have UDP frame, Aruba network encapsulation, remote mirroring, that is Aruba ERM. And then inside this, you can see the radio information, beacon frame, and information elements of the beacon frame, right? So this is how we can perform a remote sniffing by using existing tools, or we can, use something like this Aruba ERM and Python scripting. The second question was, can you uncover a hidden SSID, right? If you remember from the last session, hidden SSID is the case where you have a Wi-Fi network which is not transmitting its name, right? It is not broadcasting its SSID in its beacon frame. So instead of containing its SSID in the SSID information element of the beacon, it is blank, right? So that is the hidden SSID. And what was the need of hidden SSID? It was one kind of pseudo security measure, right? Because if you don't know which SSID it is, you cannot actually connect to it. That was the thing. So can you uncover a hidden SSID? That's the question. If a client is connected to it, then it is very, very, very easy to do. Because when a client is connected to it, before connecting to it, it has to know which SSID it is, right? Uh, and and at that time, you can actually know which SSID it is. So what you can do in this case is just turn on the AeroDump NG on the same channel on which the SSID is. Why? Because we don't want to miss any packets. So that's first step. Second step is to disconnect the client. So the client device need to be disconnected. Send a deauth to it, send something to it, right? Uh, it will be disconnected. And then when it will try to connect again, at that time it will perform a probe request, and the access point is going to respond to it. So from these frames, you will be able to tell which SSID it is. So SSID will be visible to you. So when you have a client, it's very easy to do. You can clearly do this. However, when you don't have any client, you have to rely on the dictionary attack. So what you can do in this case is you can get popular SSID dictionaries from internet. You can write an automation script which can try to connect to this network by using one SSID at a time from the SSID dictionary. And when you will use the right SSID at that time, the connection will succeed. And this is how you will know that, okay, this is the SSID name. So again, this is a dictionary attack. We know it is not going to succeed all the times, but this is the best that we have for this case. If you have a hidden SSID, and if you don't have a client that is around which is connecting to it or trying to connect to it, then you cannot do anything about this. Similarly, can you find a non-probing client? That was the next question. So what is a probing client here? Probing client is a client which is making probe requests for the SSIDs, right? Or the networks for which it had connected to in the past. That is what a probing client is. Now it is very easy to locate a probing client because you just you can just turn on aerodump ng, and aerodump ng will as soon as it will see a probe request coming in, it will actually tell you that, okay, this client is trying to perform probes. So you will be able to locate the client. However, if the client is not connected to any network, and if he's not performing any kind of probes, if he's not sending any kind of probes, in that case, you cannot tell if the client is there or not, right? There is no way for you to tell because it is not sending any packets, right? It is not sending any Wi-Fi packets, so you don't know. However, in this case, what we can do is, again, this is approach which might not work. Sometimes, it will work sometimes. So what we can do is we can find again a popular SSID dictionary, and then we can write an automation script to create networks, right? So what it will do, it will take one SSID at a time from the list. It will create a network, and then it will wait for few seconds and see if any client is connecting to it. Because if your client is just looking for the network, if he is just searching for the networks passively, and if he sees a network with SSID that it has in its PNL, its preferred network list, right? It will try to connect, and if it does, at that time you will know that, okay, a client is there. Otherwise, you won't know if it is not transmitting anything. So, any questions still here? Any questions in these concepts? If you have any questions, please let me know. Just drop those in the live instructor interaction channel. Okay, cool. So let's move forward then. In session one, if you remember, we talked about Wi-Fi. We learned about Wi-Fi protocol amendments, how to perform the Wi-Fi traffic capture as well as analysis, right? After that, we also discussed how to create honeypots using your hosted PD, basic open honeypot, right? How to connect to a network which has no security, and how to analyze its traffic, and what are the downsides, right? All of that we learned. We also talked about some of the attacks that we can do by by just knowing all of these basics. So now today we are going to discuss about the the personal network, right? But before that, let's understand why they are really needed. So till now we have learned about Wi-Fi environment, that you have access points. SSIDs or Wi-Fi networks are configured on access points. This SSID is the network name which is used for the discovery. Beacon frames are sent by the access point to broadcast its network, whereas the clients also use their probe request to look for the network. Once your client locates the network that it wants to connect to, it then exchanges other management frames and it connects to the network, right? And after that, they exchange data. That's what we have learned till now. So why do we really need secure networks? Obviously, first thing that we need is the confidentiality, right? Because when we are using a Wi-Fi network, we are accessing internet, we are browsing some websites. If we are using an open network, anyone with a monitor mode capable Wi-Fi card can actually capture all the traffic that we are exchanging with the access point. After performing some kind of analysis, right, some very metadata based analysis, uh, he can actually tell what we are actually doing, right? So if the user who is using the internet, right, if who's using the Wi-Fi, if he is using HTTP sites, then it is very easy, it is very clear what he is doing. But even when he is using HTTPS, by looking at the IP addresses and the DNS queries and responses, it is possible to approximate, right, to guess what kind of activity this guy is doing, right? There are a lot of techniques by which you can perform traffic analysis. So that's the problem, right? So confidentiality is at stake. You don't want someone to know that, okay, you are visiting this specific site, or you are trying to buy something, or like that. Second problem was access control. Because network is open, access point as well as the client, right? They don't have any way to know if the other one is the right party. So anyone can join the network, and then anyone can try to send IPv4, IPv6 messages to other clients. So you don't want that. Third thing is integrity. Anyone can claim to be the real network, because there is no way of knowing if the other person or the other device is the right party, right? And anyone can forge packets and send it to real users. So all of these problems are there, and that's the reason why we actually need secure networks, right? Once you have the secure networks, all of these problems can be solved. So let's see how we can go now about it. Okay, just a minute. I'm just turning my noise removal filter on. Okay, yeah. So in the open network, we had some pseudo security measures, right? So we have already talked about these. We had MAC filtering, which is MAC based access control, right? We also had hidden SSID, but if you have completed the labs given in the assignment, you already know that MAC filtering is very easy to bypass. Similarly, hidden SSID, we just learned that it is not going to protect us. There are ways to know the hidden SSID, and then you can connect to it. So that is why we actually need proper security schemes that can actually help us with all of these three aspects. So WEP was the first one in the line, and then came the WPA, WPA2, PSK Enterprise, and then WPA3 is the newest one that we have. WEP, or Wired Equivalent Privacy, this was the first security standard that was made available for Wi-Fi. It used so the WEP, it was designed in such a way that it used RC4, or reverse cipher 4 stream cipher, for the confidentiality, right? And for the integrity check, it used CRC32. CRC32 is the cyclic redundancy check 32 algorithm. Just like you have your MD4, MD5, right? Like that, CRC32 is a digest algo. So you provided some output, you provided some input of variable length, and then it is going to give you fixed length output. And because it is CRC32, in this case, it is going to give us 32 bits of output. And this output, right? It will be used to ensure that our data is still not corrupted, it is not tampered with, right? Just like we use MD4 and MD5 to make sure that our files, when we are downloading them, we are transferring them, are not damaged or tampered with. WEP uses 40-bit and 104-bit shared key. So you have options here. You can either go with 40-bit or you can go with 104-bit. Then we select, when I say we, it means algo, right? The implementation, it selects 24-bit IV at random. So IV is initialization vector. It is nothing but a random string, right? So this 24-bit IV is selected and it is concatenated with these shared keys to create the final key that we are going to use. So if you add 24 to 40, it will become 64. If you add 24 to 104, it will become 128. So this is what your WEP is. So how the connection flow works in terms of WEP connection. So all of this part is same, right? If you remember from our last session, first of all, the discovery phase happens, and discovery can be done by using the probe requests and responses and beacon frames. Once that is done, after that, the device, the client device, sends an authentication packet to the access point. Access point responds, and after that, the association request and association response packets, they are exchanged by these devices. And after that, in WEP, because both the parties already have the key, they start exchanging data. But in this case, instead of sending the data in plain text, they will send the data in encrypted form, right? So this is your WEP connection flow. Now, to understand how WEP actually works, right? How WEP encryption works, you have to understand the basics of XOR operation. XOR is a operation in your cryptography. It's called exclusive OR, right? You can read it as XOR. So the property of XOR is when you apply XOR on same bits, the resultant bit will be 0. When you apply it on different bits, the resultant bit will be 1. So if you check this truth table here, you will actually see when the bits are same, you are getting 0. When the bits are different, you are getting 1. Right? So this is a truth table of XOR. Now, how we perform encryption using XOR? You have this plain text. You create a secret key, and don't worry, we'll talk about how the secret key will come. So you have this secret key. You will perform XOR on these, and if you check here, right, same bit, 0, different bit, 1, different bits, 1, same bits, 0, different bits, 1, same bits, 0, right? So in this manner, you can see that you have a plain text, you take a secret key, and you XOR it with this to get the ciphertext. Now this ciphertext is sent to the other party. The other party also knows the secret key, right? Because both parties have the key. So other party will again perform this XOR operation on the ciphertext and it will get the plain text. How? Because when you perform XOR, right? If you are performing XOR on the same bits, the resultant is 0, right? So when you perform this operation this side, it is essentially canceling itself. So your secret key will cancel itself and you will get the plain text. So now here you have the first step of WEP. You take 40-bit key. For the simplicity, we are only going to consider 40-bit key, right? It works similarly for the 104-bit key also. So you will take 40-bit static key and you will then generate 24-bit IV from random, right? So it is selected randomly for every packet. For every packet, IV is going to be different. So when you combine these, it will become 64-bit, right? You will pass this to the RC4 algo, which is going to generate a random key stream for us, right? So this is acting as a seed to give us this random key stream. Random key stream is nothing but a sequence of 1 and 0 which is random. Now it looks random, but it is not really random. It is a deterministic output, right? When you will provide this specific seed here, and you will provide this specific combination here, this random key will be the same, right? So for a specific seed, the random key stream is going to be fixed. It looks random, but it is not like you will put the same key and then the next time random key stream will change it. It is not that like that, right? So when you will provide same key string or same seed, it is going to give you same key stream. Step 2 is you take the variable size data that you want to transfer, you calculate CRC32 over it, and it will give you 32 bits, obviously. We call it ICV or integrity check value. So you will take this ICV and you will then append it to the data. So this is your printx data, this is your ICV, and now you have attached it to this, right? Now next stage is that you take this random key stream and you take this data concatenated with ICV and you perform XOR on it. And when you perform XOR on it, it will give you ciphertext. So this is your ciphertext, this much. How you have generated the ciphertext? You had this random key stream that is generated by this RC4 when you are providing it a specific seed, and you are XORing it with the data and the ICV. So once you have the ciphertext, half of it is done. Now you take this IP from here, you add padding to it and key ID to it, and it will be attached to this packet and it will be sent with the packet. So this is now your payload, right? So yeah. So if you again check this diagram here, you will actually see that this is IV. This is your static WEP key. You're passing both, and here you're actually getting this seed, right? So this is the combination of IV and WEP. It is acting as a seed. You are getting the key stream here. Similarly, here you are taking the print text. You are calculating CRC32. Then you are appending this ICV with the print text, and here you are performing XOR of key stream and the plain text, right? So it is giving you ciphertext. You're taking IV from here, you're adding some padding bits to it, you're adding key ID to it, and you're attaching IV here. And all of this will be packed into the frame body. So if you remember this structure is your packet WLAN frame. This is your WLAN frame. This is your WLAN header, and this is your frame body, which will contain IV, data, and ICV in encrypted form, right? And then you have frame check sequence here. Now, important thing to notice here is your IV here, right? It is again made up of three things. First 3 bytes are of initialization vector, that is 24-bit. After that, you have 6 bits padding bits, and these padding bits are 0. So you have 0, 0, 0, 0, 0, 0. And then you have key ID, 2 bits of key ID, right? And all of this part is unencrypted. This part here, data and ICV, it is encrypted. So now this frame, when it will go over the air, uh, any adversary, he won't be able to see what is inside this part, right? And that is the objective. That is how we are providing confidentiality in the network. Now, what is key ID here? So whenever you actually define a web network, whenever you are setting up a web network on your Wi-Fi access point, right, at your home, you'll actually see when you are trying to configure WEP, it will actually ask for 4 keys instead of 1. So you can define the 4 different key here. Now, when you are using it, you can use any one of these 4. So for example, here you can see we can select which one we want to use. So these key ID represents which key is being used for encryption of a packet. So we have 2 bits there to represent the key ID, because you have 4 in total, right? And we start counting from 0. So first one can be represented as 00, second one can be represented as 01, then 10 and 11, right? So this key ID will tell the other party that, okay, the third key or the second key or the first key is being used. So let's take a look at the walkthrough of WEP connection. So first of all, whenever we start with analysis, right, always try to start it from the wireless WLAN traffic, right? From here, it becomes very easy to view all the network traffic, from a high level. So we can see, which network has how many clients connected to it, what kind of data it is transmitting, right? So what kind of frame it is transmitting more, all of that we can see, and then we can easily, find the network that we want to attack. So it really helps in drilling things down. So in this case, we know that we are talking about WEP network. So this victim network, right, which is using WEP, this is the one that we are interested in, right? So there it is. And if you maximize this part, it will actually show with which devices it is exchanging packets. So this itself, it is the BSS ID, then these are the clients, right? This is also a client. So now we are applying a filter. Sometimes Wireshark make mistake, with filter when you do this. So you can see here that half of the filter is correct, right? We want to apply the filter on the BSS ID. However, this half is totally wrong. We don't want to apply it on SSID PANet, right? So we can just remove this part. And now when we will hit our enter, we'll actually see all the packets that are related to this specific BSS ID. We can see the beacon frames, the probe responses, and all other frames. Now we are not interested in seeing a lot of beacon frames and your probe requests and probe responses. So we can actually take them out. We can ignore them, or we can filter them out from the traffic. All right. So for that, we can select. So for that, we can just select the type and subtype, and we can just select not selected, right? And when you do this, now you can observe that there is no beacon frame, right? Because of this filter here. So we have filtered out the beacon frames. Similarly, we are also going to filter out probe responses, and that is enough, because now we can clearly see the authentication packets, the association packets, and the data packets. This is the first packet sent by the device to the access point. You can tell that from the sequence number, that is 1. If you check the next packet, it will be sequence 2. And then you have your association requests and responses. And after that, if you check the data packet, that is where you will find interesting things. So data packet in this case, if you maximize this, it will only show you this blob, because Wireshark is not able to make sense out of it. It is, And you can also confirm that it's a web packet, that it's a web encrypted packet by checking the web parameters here. So you can observe IV or initialization vector, right? That is 24 bits long. The key index or key ID is 0. And then you have ICV. Again, this ICV is encrypted, right? It is not in plain text format. But yeah, we have ICV, we have key index, and then we have initialization vector. So this is a web encrypted packet that we are seeing. If you want to see which part of the packet is where, you can just select that part here, and the corresponding values and corresponding place in the dump will be highlighted. So here you can observe key index, right? So this is padding plus key index. This is your initialization vector, and then this is your data, encrypted data. Right. So this was your web packet walkthrough. Any questions still here, guys? If something is not clear, just let me know. Okay. So let's move forward. So now one question can be why it is important to send the IV in plain text, right? Why you are even sending it? And even if you have to, why you are sending it in plain text, right? Why you are not hiding it by encrypting it and right, like the other ciphertext? Uh, because IV is needed for the decryption also, right? So if you remember, in the decryption routine, in order to generate the same key stream which will be used to decrypt the packet or the frame, you will need the same seed phrase to be passed to RC4. Now WEP key, that is your 40-bit WEP key, is already available with the other party. But IV is not available, right? And IV is needed to create the seed. That's the reason why IV is sent with the packet and without any encryption. So IV will be taken from here. Web key is already with the other device, and then by combining these, the seed will be created. Seed will be given to RC4, and RC4 will then generate key stream. And this ciphertext will be taken from here. It will be XORed with the key stream to get the plain text. Now plain text will be sent directly on this line, right? So plain text is sent. Now ICV is also taken because you had plain text data and ICV. So ICV you have taken. Now you again calculate the plain text CRC32. So you get ICV dash. Now you compare if this ICV dash is equals to ICV, then it means the packet is not tempered, it is not damaged, right? It is not corrupted. Whereas if it is not same, then there is some problem. And then you can request for the retransmission of the packet. So in this way, your web encryption and decryption works. Web is broken, right? We all don't know there were multiple researches that people did over the time, and people had told in 2001 itself that web is completely broken and should not be used. However, over the time, the attacks also improved. So now it is so easy to attack your network and crack the key, irrespective of what key it is, that it is very it is actually futile to use web. So why the problem with web is there, right? What's the reason behind the problem? The problem is that the IV that we are choosing, right? It is a relatively smaller address space, or it is a relatively smaller space in which you can only have 2 raised to 24 possibilities, right? So 3 bytes comes to 24 bits, and if any every bit can be either 1 and 0, that means there are two values for each bit, right? 0, 1. So if you calculate the possibilities for all 24 bits, the total number of possibilities will be 2 raised to power 24, right? Or 16.777216 million, right? So that's the thing. That's the problem with IV. It is due to IV's size. What happens when due to the small address space? So this can be explained by using the pigeonhole principle. Pigeonhole principle states that suppose there are 10 pigeons and there are only 9 holes, right? So when the rain will come, right, or when the pigeons will go to sleep in the night, there will be one hole in which there will be more than one pigeon. Why? Because pigeons are more, pigeon holes are less, right? So obviously it is going to happen. On similar lines, there is this thing called birthday paradox. So birthday paradox actually says or states that okay, there are 365 days in a year, right? So the possibility that if a room is there and if you have 366 people in the room, then with 100% probability, two people in the room are sharing the birthday, right? Not the year, but month and date. So it is very clear and very simple to follow, right? If you have 366 people, you have 365 days, then it is obvious that one of the person is going to share his birthday with other person, right? It is 100% probability. Now, by playing on this probability, you will be amazed that even with 23 people in a room, there is half probability, that is 0.5 probability, that two people will share the birth date. That is the birthday paradox. So the thing that we are trying to show you from the birthday paradox is that for 100% accuracy, or for 100% probability, or for 100% probability, that is probability of 1, you might need a lot of samples, but this relationship is not very predictable and not very is not very linear, right? It's not linear. So even with 23% people, you can actually say that with half of the probability, there are two people in the room who will actually share the birthday, right? So that's the birthday paradox. So by using the birthday paradox and the pigeonhole principle on this IV thing, it is obviously it can be concluded that for large number of packets, the IVs are going to be reused heavily, right? So in normal sense, we can always say that okay, 16.777 million is a very big number, right? To repeat. But because these IVs are not selected sequentially, these are selected randomly. So even when you have way less values than this, way less frames than this, uh, there can be repetitions of your IVs. So you can say that, okay, if that is the case, then you will at least need 16.7 packets to crack it, right? So, but no, because you are choosing these on random. So a repetition will happen before this. And by applying the modern methods that uses weak IVs, we can actually even crack the 40-bit web key, right? That is written as 64 here, uh, in way lesser packets, right? So that's the thing here. Now, idea here is you will need large amount of IVs, and with modern methods, it will come around to say 25,000 to 40,000. And again, it is not very predictable, right? Because you don't really know when you are going to get a weak IV. and your latest methods, they use weak IV method, right? They use weak IVs to recover the key. So the idea here is you are going to collect a lot of packets, and from those packets you are going to get IV, and IVs will be then used to recover the key. That's the whole idea about it. So to capture the packets, to capture a lot of IVs, how you are going to do this? There are two ways. One way is the passive IV capture. Passive IV capture means uh, the network is in operation, right? The clients are connected to this network and they are exchanging some data. So as an attacker, we will not participate in it. We will just sit there. We will put our card into monitor mode, and then we will start capturing the traffic. We will fix our Wi-Fi card or Wi-Fi adapter onto the same channel on which this access point is operating, this WEP SSID is operating, and we will then capture it. So that is the passive part. Now, the good thing about passive IP capture is that no one will actually know that you are there, because you are not transmitting anything, you are just capturing. So it is very stealthy. The problem is, uh, if you don't have a lot of clients, right, it is going to take a lot of time to capture the number of packets that you want, right? So that's the downside. And if you take a lot of time, it might be possible that the client might leave, and it is also possible that the password is changed, the web secret key is changed, right? So that's why if you want to do it in less time, you can use active IV capture. It is fast, but obviously because you will be doing packet injection in this, it is detectable. If you are using some kind of a wireless intrusion prevention system, or if there is some kind of monitoring, this injection will be noticed, and someone will know that okay, someone is trying to crack our WEP network. So what we will do in the active IV capture? In active IV capture, we are going to inject specific traffic packets, right? Which will then again lead into generation of more packets. And how to do that? Now, thing is, you cannot directly inject, right? Because it's a protected network. It's a WEP protected network. As an attacker, as an outsider, we don't know the static key, the web static key. And if we don't have that, we cannot create a valid packet and send it, right? If we create any other packet, it will be directly rejected. And then there will be no replay, right? We won't be able to do anything. So what we are going to do in this case is we are going to capture the R packets that are the part of the network already, and we are going to send these R packets to the access point. So when access point will get the R packet, it is going to respond to this, right? Either the access point or the device, other devices to whom this R packet is going will then respond. And when this happens, because those devices, right, all of other devices which are the legitimate users of that network, they do have web key, right? So all of the packets that they will send in the response will be valid, and they will have IVs, and that is what we can then capture. But again, the problem comes, uh, it's an encrypted network, right? So how would you know that it's an R packet? How would you know that it is the packet that you need to send? So before moving to that part, if you are if someone is uh, not able to recall what ARP is, ARP is address resolution protocol. It is used to know the IP address to MAC mapping, right? So what happens is, suppose this guy here, this machine here, it is making ARP request, right? So it is going to ask which machine has this specific IP address, right? And this message is actually a broadcast. So it will be sent to all the machines that are part of the network, right? And which machine, the right machine which will have that specific IP is going to respond. So here you can observe, this guy sent ARP request, ARP request went to both of these machines. But now here in this case, this machine has the IP address that is mentioned in the ARP request. So this guy is responding that, okay, I have this IP, right? This is how it looks in the capture. So this is the device that is making the request. This is the ARP request. You can see it's a broadcast request, right? So it says who has this IP, right? Tell this. Again, this is the interpretation of Wireshark. Uh, in reality, this is how it will look, right? So this ARP packet is going to have sender MAC address, obviously, sender IP address. The target MAC address is going to be blank. Why? Because we don't know, right? We don't know. That is what we are trying to figure out. And which target IP we want to figure out? This one. Our machine wants to know what is the MAC address of this machine. That is the ARP packet. So when this is sent, you get something like this as the response or ARP reply, right? And in this, you will get the sender MAC, sender IP, target MAC, and target IP. So now you know that, okay, 192.168.3.1 is at this MAC address. So when this packet comes back, the sender will actually, the sender of the request will update its MAC ARP table, and then then it does not have to again ask this same question, because now it knows this mapping is needed to transmit the packet. So what we are going to do in this case is we are going to look for any packet that looks like an ARP packet. And how we can do that? Because if you see here, right, check the length. The length of the ARP packet is same, right? It is not changing. So that is what we are going to exploit here. We will look for ARP packets which are of the fixed unique size. Once we find any of these packets, we will blindly replay it. So this is the attacker, this is a client, this is access point. Maybe a ARP request is going through the traffic, because our attacker here, right, it is capturing all the traffic, it is inspecting all the traffic. It will look for the packets which are of size of a ARP packet. Once it finds such a packet, it will blindly again retransmit it. So this packet will be sent to access point, and if this is a valid ARP packet which has the corresponding machine available on the network, the access point is going to send a response, right? Either the access point or the other clients, but that will also come through the access point, right? So if that happens, then you will get a packet in response, right? And that is what we are looking for. So any packet that looks like our packet will be resent by this attacker. And when it will get a reply, when it will get a response, it will know that I have played the right ARP packet. That is how it will know. There is no other way for it to know, because all of the packets are encrypted. It cannot tell you which one is the correct one, which is not the correct one, but it can transmit and then it can wait. If the response comes, then it will know that, okay, we have found the right ARP packet. And once that's happening, start sending this packet again and again and again and again till the time you have enough packets to crack the web. So here you can observe, right? This packet is sent here, response is coming, packet, response, packet, response. Now you will send it like 10, 15, 20,000 times. And once you have enough packets, you can then crack the web. Now you don't have to do all of this finding the ARP packet, injecting this, retransmitting it on your own. There are tools which are developed for this specific purpose, so they will actually do this for you. And we're going to use Aircrack NG Suite heavily for this purpose. Aircrack NG Suite is a set of tools. There are multiple tools in this set, right, which you can use for different purposes. First of all, for monitoring, we use AeroDump NG and AeroMon NG. AeroDump NG we have already used. Airmon NG is used to set your card into monitor mode. You don't really need it if you are comfortable in using the IWDEV command, right? That can also do the same thing. For attacking, we use airbase and air replay. So airbase NG is used to create fake honeypots, right? Not fake honeypots, but directly honeypots or fake networks. You can also use HostAPD for this, right? We have used HostAPD in the last session because it is way better, it is way more flexible, and it is way more stable. Air replay NG is the one that is used to send deauthentication packet. It will be used to retransmit the packets, and for ARP replay also we are going to use air replay NG. And then comes the aircrack NG itself. It is the software that you use to crack WEP and WPA PSK, right? So we have covered till here. Now the next question comes, when you were dealing with an open network, it was very easy to connect to this open network by using your CLI based tools, right? You were just using simple CLI based tools and it was connecting. But how the connections will work now when you have encrypted networks, right, or secured networks? So WPA supplicant is the answer for that. WPA supplicant allows a Linux machine to connect to encrypted network. And how it works? You have to create a WPA supplicant config. This is how a WPA supplicant config looks like. So you have network defined here, right? Scan SSID means the client is going to send probe requests for this specific network. This obviously is the network name or the SSID. Then you are defining the WEP key, right? So you can see WEP key 0 is this, right? Similarly, you can define WEP key 1, 2, 3, 4, right? Uh, Actually, not 4, 0, 1, and 1, 2, and 3, right? Only 4 are available. And you can define the keys in those. And then you can select here which key to use. So if you remember key index, right? This is the same thing. So here you are defining which key to use. Once you have created this, after that, you can then run WPA supplicant and you can provide this configuration file with the interface name and it will try to connect to your secure network. Now, just like your HostAPD, you don't really need to remember all of these configurations, right? Your WPA supplicant and HostAPD, they have these sample configuration files hosted online. So you can reference to these. These are the master configuration files. And from these, you can see, what you will need and which parameters are there and what are the possible values, right? So don't really need to remember these till the time you can access these samples. So let's check how to crack WEP and how to connect to the WEP enabled SSID. Yeah, so this is the one. This is the lab. Once you are inside the lab, right? So the first step that we take is we list all the interfaces that are there in the lab. So here we can observe we have two interfaces. First interface is the WLAN 1 and then you have WLAN 0. Both the interfaces are currently in the managed mode, right? So first what we will do, we will put the WLAN 0 in monitor mode. And we can use IWDEV command for it. Once you have done this, you can check the type here. This type will turn monitor, right? First it was managed, now it is monitor. But still you can see that it is not showing any other information. It is transmission power is 0, right? The channel information is not visible. So you have to turn it up using ifconfig WLAN 0 up. You can do that, or you can directly run aerodump ng WLAN 0 on it and it will automatically turn it up. So once you have executed the aerodump ng, right, your your interface WLAN 0 is jumping on different channels, and it is actually showing us all the SSIDs that are available here. And we can also clearly see that Epic Media Corp is the one that is using WEP. And this is the one that we are going to target. So we know this, we know that it is on channel 6, right? You can observe here, it is operating on channel 6. So now, because we want to capture the traffic for this specific SSID, we don't want to capture traffic of others. So we are just setting it on channel 6 because that is, what we need. And we are also going to write these captures into a capture file. So now you can observe that the channel is fixed to 6, and we are able to see the traffic from channel 6. Here we are seeing traffic from channel 1 because, as you know, these are emulated labs, and this was a bug in the system that we have used, right? So it is showing us traffic from channel 1 also, but otherwise in real world, it will only show you channel 6 when you have fixed your interface on channel 6. So this was the evil cop, right? This is the BSS ID. Now, if you check here, you will see that there is this client that is connected to this network. Please remember, for this approach, you will need at least one client connected to the access point. If the client is not there, then you won't be able to find the ARP packet, and then you won't be able to do anything. So you need a client here. And then what we are doing then is uh, we will now try to look for the ARP packets, and then we will try to replay those. So -3 here signifies the ARP replay attack. -B is to define the BSS ID. -H is to define the client MAC, right? And then you have your interface that is in monitor mode, that is WLAN 0. Now, what is the need of defining the BSS ID and this client MAC here? Because first thing, it needs to only look for the relevant traffic, right? Because it is looking for the traffic, and it is then trying to find the ARP frames. That's first thing. And after it has found that, it need to replay it. So that's why this information is important. So you define it and you run it. Now you can observe that it is reading the packets, but you are not seeing anything here, right? Because till now it has not got any ARP request. So again, it is reading more and more, and there you go, right? As soon as it got some ARP request, now you can observe it says sent 226 packets. So once it gets a ARP request, now it is sending it again and again. And because it has found the right one, we'll actually see that the packet count will go up drastically. So that's what you can observe here, right? So you can see the data frames 2861, and it is increasing drastically because your air replay is sending ARP packets or ARP frames at very high speed, at very high frequency, I should say. So yeah, and again, frequency means sending a lot of packets in less time, not the other frequency. So once you have enough packets, right? In this case, we just use 12,000 packets, but it is advisable that you use 25,000 packets. You can run aircac-ng on it, right? You have defined the capture file here. This is the capture file in which the packets or the frames were being saved. And here it is now giving you option which SSID you want it to crack, right? Just because it is showing us, it doesn't mean that it can crack others also, but it is just giving us option. So obviously we want to go with the first, we want to go with the fourth one, right? That is the WEP. So let's provide it the number 4. And now it will start, cracking this. And once it is able to crack the key, it will then show us the WEP key. And there you go. This is the hex representation of the key. This is the ASCII representation of the key, right? So it is decrypted. And now what you can do is you can create a supplicant file. Just a minute. You can create a supplicant configuration. You have scan SSID 1, SSID name is mentioned, the web key that we figured out is mentioned, and after this, we can then use the WPA supplicant with WLAN 1 interface, right? So -B here, it signifies that it will run in the background. Then we have defined the interface here, and then we have defined the configuration file. This is the driver that is being used in this case, right? Netlink 802.11. Again, a lot of people make mistakes of confusing this driver with the driver that is needed to operate your interface. These are different. This is the driver that your WPA supplicant is using here, right? So now if you check the IWDev output, right, you will actually see that it is in managed mode, but it is not connected yet. So wait for a few seconds, try to do this again, and this is when you will actually see that it is connected to this SSID. It is on channel 6, it is in managed mode, right? So now you have connected to the web network. And then the next step should be to get the IP address. If the DHCP server is running on the access point, which is the case in most of the scenarios, you can directly use DH client -v interface from which you want to send this request, and it will send the DHCP requests. And if there is a server, DHCP server running on the network, you will actually get a IP address like this. And now you have IP layer connectivity, and then you can perform scans. You can then send traffic to other clients or other devices. So this is how you can crack WEP. Guys, any questions from your side? If it is not clear, if some part is missing, right? If you are not able to understand it, just let me know. If everything is good, then we'll move forward, and then we'll take a 5-minute break first, and then we will move forward and cover more stuff. Okay, great. So guys, let's take the 5-minute break, and after that we'll again meet and we'll cover the remaining stuff. So let's continue with the remaining part. So we have recovered the web key, right? So what after this? Obviously, once you have the web key, you can connect to the network. Once you have the IP layer connectivity, just like we saw in the demo, by making the DHCP requests, you can get the IP address, and then you can interact with the devices, the machines, the services, right? You can run your Nmap and all of that. So proper pen testing can be done after that, right? That's one way of doing it. The another way is that you can decrypt the traffic for other devices because the key is same, right? So for web, the static key is for all the devices, it is same. So you can capture the traffic for other devices, and then you can use Wireshark or Air Decap to decrypt it. And after decrypting, then you can analyze it, you can see what they are doing, right? And you can try to find some valuable information, depending on what your perspective is. If you have a graphical user interface at your disposal, Wireshark will be the easier one to use. So let's see how to use Wireshark. Again, it's very easy once you know how to do this. So you open Wireshark, you have web packets here, and you can even make sure of that by applying this filter. So this filter is going to show you the web packets that are there. All of these packets are using web encryption, and for this, this protected flag is actually set on these. You can also see the web parameters, IV, key index, right? All of these. So now what we want to do here is we want to decrypt all of these so we can have a visibility inside of this data. What are the above layers, right? What kind of activity is being done? That's what we want to do. And we are assuming that we have cracked the web key, and we already have the key with us. That is our assumption here. So what we did here, we actually applied filter by BSS ID. So we can see all the traffic that belongs to this specific BSS ID, right? So this is the filter here. And once you have the filter, after that, we can see all the packet flow and then the data traffic, right? So now we can go to edit. From there, we have to select preferences. And from here, we will select the protocols, right? In protocols, look for IEEE 802.11. As we know, that's the Wi-Fi standard. When you will select this one, it will actually show you these options on this side. So here you have to enable the decryption. Just make sure that this checkbox here is ticked. And in the decryption keys, click this edit button. It will open up this specific box. And in this, you have to then create an entry for your key. So because we are using web key, we will use web from the dropdown. And here we will define the web key in the hex format. And after this, just press OK. Again, press OK. And now Wireshark will reload again. And this time you will be able to see the decrypted packet. And there you go. So if you clearly observe this, right, you will see that it is showing us that it's a UDP multicast domain name service query. However, it was a 802.11 QoS data, right? So now you can observe that this data packet is decrypted, and we can, we or the Wireshark can actually look into the data, right? And we can actually interpret it, and we can see that, okay, these are the higher layer protocols that are there, right? You can also see the ARP packets here. And one more thing that you can see here now is web ICV is correct here, right? It says it is correct. Why? Before it was not saying correct. Before decrypting, you cannot know if it is correct or not, because your web ICV is also encrypted with the plain text data, right? But when you have decrypted it, the ICV is also decrypted, and we are currently seeing the decrypted ICV. And obviously, you have the payload decrypted, you have the ICV in plain text form. So what you can do is you can actually run CRC32 on the plain text. You can find the ICV, and then you can match that ICV with this ICV that is shipped with the packet. And if it is same, then it means it is correct, right? The packet is correct, packet is not damaged or tampered with. So this is how you can decrypt web packets using Wireshark. If you don't have access to a graphical user interface, right? If you only have access to CLI and still you want to decrypt it, you can use AirDecap NG. AirDecap NG is very easy to use. You use AirDecap NG command. Dash W is to define the web key in hex format. And after that, you give it the PCAP in which you have stored the web traffic. It will read it, and then it will show you that, okay, it was able to find 22 web data packets, out of which it was able to decrypt 22 packets, right? Now, again, in this case, there were 22. In your case, it can be different, right? Uh, and you will able to find a decrypted PCAP file, which will be created by this AirDecap, right? This is the one, web02dec.cap, right? Dec stands for decrypted. And then you can use Tshark or TCP dump or any other tool to then analyze this specific decrypted PCAP, right? So here we are using Tshark. Tshark-R will actually show you the packets. Here in this case, after decrypting, we are able to see that, okay, this UDP packet is there. And then we can use TCP dump or Tshark itself to find more details about this packet. This is how you can perform the decryption as well as uh, I'll say analysis of the packet using the CLI tools. Okay. So now this approach, right, that we just learned about, uh, the main thing is it is dependent on the access point. You need access point to be in the vicinity to perform this attack, right? So attacker need to be in the range of the access point. You can think of a hacker that is sitting in parking, or you can think of a remote hacking device that is deployed at the place and attacker is using it remotely, right? So if you think about it, right, the remote sniffing that we were talking about in the beginning of this session, it can also be done using a remote hacking device that can have a 3G or 4G connectivity. And over that connectivity, the attacker can actually sniff the packets at some place and then process them at some other place. He can even launch these attacks remotely, right? All of those things are possible. Or if you are if you are sitting on the top of some building that is like 1 mile or half a mile from that target building, you can even use a parabolic antenna and you can pick up the packets and all. But you need to be near it, right? You cannot hack random people at random places. That is what the limitation of this specific attack is. However, that is where the access point less attacks will be introduced, right? You will be able to use these attacks when you don't even have access point nearby and you only have a wandering probing client. So wandering probing client is the one which is not connected to any network, but it is actively looking for the networks that it has connected to in the past. So this cafe latte attack for AP-less web cracking was actually proposed by Vivek Ramachandran. He's my boss. He had proposed this in I think in 2007 or 8. So at that time, he presented it, in the conference. This is the link for the actual talk. If you want to see this, you can check it out after the class. Uh, so we have to understand one main thing that actually made this available, actually enabled the APLS attack. So that thing here is due to the way your WEP is designed, right? It is possible to change the encrypted data and at the same time change the encrypted ICV. It is possible in some cases, right? That is what this complex looking application, sorry, this complex looking equation is actually conveying, right? So you don't need to understand this actually. The thing that it is trying to convey is it is possible to modify the encrypted data and then modify the encrypted ICV accordingly, so that when the other party, after receiving this specific frame, will not be able to tell if it is tampered or not. It will look like a legitimate frame to the other party. That's the crux of it, right? And now, how is this being done? So suppose this is your encrypted data, this is your encrypted ICV, right? This part, if you remember from our web encryption process. If we have to define it in terms of data and plain text data and key stream, we can say this, right? Because this is how you have created the encrypted data. You have taken the data, you have XORed it with RC4 key stream, and you got the encrypted data. Similarly, ICV was the CRC32 checksum of this data, and you have then again XORed it with RC4 key stream, and you have generated encrypted ICV. So you can write this part as this, right? Now, suppose this is encrypted data and we make some modifications to it. So you have captured the packet and you are making some modifications. Now the problem is, because you have changed the encrypted data, if you don't change this encrypted ICV here, uh, when this packet will be decrypted, the ICV will not match and this packet will be discarded, right? That is how your encrypted ICV is protecting against the tampering of the packet or even the corruption of the packet, right? But if you make some modifications to this encrypted data, and then if you again calculate CRC32 of this modifications, right? This modified data, you take it, you calculate CRC32, you will actually get ICV patch. And if you take this ICV patch and if you take this attacker modification and if you XOR it with the real packet that is there, what you will actually get is modified encrypted data and encrypted ICV, which is again a valid encrypted packet. So this is what this complex looking equation is trying to tell us. Now, what are the ramifications of this? The ramifications are you can actually modify the packet and this packet will be accepted by the other party, right? So that's a problem, right? And how it is happening? Because again, you can represent your encrypted data and encrypted ICV in this way, right? And if you XOR it with attacker modifications and ICV patch, you can also write it like this, right? So what you are doing here is you're taking attacker modifications, ICV patch, and data and ICV, right? So first these two will be XORed and then it will be XORed with the RC4 key stream. And when you do this, the output will be a valid encrypted packet, right? That is what it is. That is how it is working, right? Because you are actually getting modified data and corrected ICV first, and then you are encrypting it to get this. So it's a valid packet. So now we can use this thing to perform the APLS attack. What are the repercussions of this? As I already mentioned, we will be able to modify arbitrary data in a web packet, and then we will be able to patch the ICV. So due to this, the web packet will be valid and it will be accepted by the other party. And this should not happen, right? It is not wanted. It is not something that you will desire if you are using that network. As an attacker, obviously it is helpful for you. In the cafe letter attack, what we will do, we will use this property to find a GRAT ARP and then to modify this GRAT ARP, right? And by modifying it, then we will be able to create a ARP request packet, and then we will send this ARP request packet again and again and again to generate more data. Again, more packets, which means more frames. More frames means more IVs. More IVs means we can crack the web key. So what is the GRAT ARP? That's the first question, right? And the power of this attack is because you can perform it anywhere. You just need a client, and that's all. Because web key is stored on the client. Whenever you connect to any of the networks, right? Whenever you connect to any of the Wi-Fi networks, your devices actually store the key and the properties of that network. On Windows, you can actually use netsh wlan show profile name of the network to see all of this, right? Even if you add key is equal to clear in front of it, you will be even able to see the plain text key of for that specific Wi-Fi network. So because it is there, uh, what can happen is your network, right? This is the client. It is probing for security tube network. And as an attacker, we will create a honeypot that will actually respond to this. So once it responds, this guy will try to connect, right? It will send the authentication request. It will send the authentication response. Then the association packets will be exchanged. And now this guy will start sending data, right? Because this is how the web packet flow works, right? You exchange these packets first, and after that you start sending encrypted data. Now suppose, what's the GRAT ARP here? GRAT ARP is a ARP that is sent to tell other parties, to tell other machines that I have this specific IP address. That is what GRAT ARP is, right? So now we are considering that this guy here, this client here, it is not using DHCP, but it is configured with a static IPv4 address. That is what we are considering here, right? So suppose it is using 5.5.5.5 as IP. So now it will send GRAT ARPs to the access point, right? This is how a GRAT ARP will look like. So this is the GRAT ARP. You can observe here, sender MAC is given. Sender IP is also mentioned. Wherever target MAC is not mentioned and target IP is same as the sender IP, right? This is how it looks. So it is the GRAT ARP. Now thing is, this is the packet, right? You can see this is your encrypted GRAT ARP. In this, you have sender MAC. This is the sender MAC here, right? You have sender IP, and then you have target IP. And just forget about the target MAC for now. Sender MAC, you have some value in it, right? We don't know what value it is because the packet is encrypted, right? But what we can do, we can actually XOR it with FF, anything, right? Anything you can XOR it with, and this MAC will change, right? The sender MAC will change. Similarly, the sender IP also, we will XOR it with something, and the sender IP will also change. Now it is encrypted, right? So we don't know how the change will, but if we take an example of 5.5.5.5, if it was 5555, when we XORed it with FF, it will become 250 here, right? So it becomes 5.5.5.250, and target IP we will remain the same, right? We will keep it the same. That is 5555. So what happened now? Your GRAT ARP actually became ARP request. How? If you remember how the ARP request was, uh, you just need to change these two things. So it looks like that it is coming from other device and it is coming from other devices IP, right? So as an attacker, we will send this packet, this modified packet. So we took the 5.5.5.5 packet, which is a valid packet, right? That is coming from this guy. This client has valid web key. So whatever packet it is sending, it is a valid packet. So it sent that packet to us. We as attacker, we don't have web key, right? So we cannot create our own packet, but we can modify the packet sent by this guy. So we modified it and we created a ARP request out of it by making that modification. And when we send this packet, because it will look like a ARP request that is coming from a guy on this IP, and it is coming for this guy. And this guy has this IP, right? So it is going to respond. So it is going to send ARP responses, and this same thing will going to happen again and again and again. And once you have enough packets, you can then crack the WEP key. So that is how your cafe latte attack will work. Any questions still here? Is it clear? Do you want me to repeat it or explain, some part of it? Please let me know if it is not clear. I can again explain it to you. Okay, cool. So similarly, some of the vendors, they came up with another technique to protect web. So the basis of this protection, it's called web cloaking, right? So the basis was that your tools which are there to crack the web, they are using some kind of algos in them, right? So mostly they are using some kind of statistical analysis to perform this decryption. So if somehow, if we can add fake web packets in the capture that they are making and analyzing, then they won't be able to work, right? And this protection, right, so it actually worked against these tools. So aircrack, it won't be able to crack the packet when web cloaking was enabled. So web cloaking was nothing but in addition to the legitimate web packets, the the sensors that are deployed there, which are mostly the wireless intrusion prevention system, so those will also going to put in some fake web packets, right, which are again fake. They are not related to this network. They are not even, they are valid web packets, but they are not related to the web network that is operating there. But when the attacker will come, when he will use his tools, due to these fake web packets, he won't be able to crack it. But again, there was research, and it was proved that web cloaking is not actually enough for protecting the web. So this is the link for the original talk, so you guys can actually look into it if you like to. But the idea here was that if you apply, if you provide the web data and if you add the SHAF here is nothing but the spoofed web encrypted frames. These are the fake web encrypted frames, which will look like that they are similar to this web frames, the real legitimate web network, but they are not. So when you add both of these, the tools like AirCrack, they used to fail. But you can actually apply different kind of filters to remove the SHAF. And once you do that, after that, you were able to decrypt the web again. So the thing is that even after applying such methods, it was not possible to protect web, and we needed a better security scheme, right? And that is where the WPA PSK was actually introduced. So in WPA, it was an intermediate solution that was, proposed by Wi-Fi Alliance. So problem was that WEP was broken. It was known that it is not able to, protect the network anymore. But most of the devices that were out there, they were using the WEP compatible hardware, right? So it was not possible to make a drastic change, because if you do that, then the existing hardware will actually be useless. So it was decided that for now, let's decide on an intermediate transient scheme, and let's use it till the time you don't have enough time to make a drastic change. So that is where WPA came into play. it uses TKIP, and TKIP is again based on WEP, right? So it uses WEP in this. But the only thing that it changed was instead of using static keys, it used dynamic keys, and we will learn how to do that. So with WPA, the good thing was that you don't need to change the hardware, but you can just change the firmware and it will work. And that's why WPA was deployed. WPA2 was a long-term solution. Instead of using WEP TKIP, it uses AES encryption, right, in CCMP mode. And because it uses AES, if you want to do AES encryption, right, and if you want to do it faster, you need hardware changes for that, right? You need hardware support for AES. So most of our computer chips, most of our smartphone chips, they do have hardware-based AES encryption support, right? That's why AES, you will find AES in most of the places because of this support, AES works really well, right? So in WPA2, AES was used. And then there were two variations of it. One was for the personal network, and the other was for the enterprise network. So in web connection, this was the packet flow, right? You discovered about the network. After that, you exchange the authentication and association frames, and then you directly start sending encrypted data, right? So you are sending this data here, and because both of the parties have this web key with them, they can decrypt the data and they can encrypt the data, and anyone who does not have this key won't be able to know what is happening. But the problem here is with the static key, right? Because you have the static key, and that's the reason why you needed the IVs, right? The initialization vectors. And due to that, then the IV space was small, and then you have the weak IV problem, and all of those problems then led to the fall of WEP. So in this case, people wanted to avoid using the static keys, and that's what they have done in WPA and WPA2. So in WPA WPA2 PSK, after you exchange all of these packets, right? After you do association packet exchange, uh, there is additional steps to generate dynamic keys, and then the dynamically generated temporary keys are used to encrypt the data. So you are not using the keys directly, you are using the key to generate the temporary key, and then those temporary keys will be used for encryption. That's the main difference between your WEP and WPA PSK key generation and key usage. So in your WPA WPA2, what pre-shared key PSK, that is WPA WPA2 PSK, you have a passphrase. The passphrase needs to be 8 to 63 character long. That is the requirement. It cannot be less than 8 character long. It cannot be more than 63 character long, right? So you will take a passphrase, and this is the network shared passphrase in this case, the secret passphrase, which will be available on the access point. It will be available with all the clients and users who are authorized to join this network, right? So you take this passphrase, you pass it to PBKDF2, that is password-based key derivation function 2, and it will give you a pre-shared key of 256-bit. So this is your human-friendly, human-readable password, right? You pass it to this specific function, and then it will give you, a random collection of one and zeros, and it will be used as the pre-master key. That is 256-bit key, right? The same thing is done on the access point side also, right? Because you feed the passphrase in access point. Access point will then derive the PSK or the PMK here. Sorry, it is the PSK, and PSK is derived on this side, right? Now, what is PBKDF2? PBKDF2, it takes the passphrase, the SSID. This is the passphrase, right? The Wi-Fi password, as we like to call in normal terminology. Then you have the SSID, network name. Then you have the SSID length. And after that, these two parameters are constant. So first parameter is the number of iteration, which means this is the number of iterations that this function will actually iterate and before generating the PMK. And then 256 is the intended key length, right? So this is the length of the key that this function is going to give. So it is giving us 256. So you have 256-bit PMK. So once you have this PMK on both sides, right? From this PMK, then you have this PMK on both sides, 256-bit, 256-bit. Now you want to use this PMK and some other information to generate the temporary keys. You don't want to use this PMK directly for encrypting, because if you start doing that, then again you are going down the path of WEP, right? So you don't want that. So what happens here is, once you have exchanged the authentication and association packets, after that the access point sends message 1 of a handshake that we like to call four-way handshake. It's called four-way handshake because there are like 4 packets that we are going to exchange in order to generate and share the secret temporary keys, right? So in message 1, this access point will generate anons. Anons is nothing but a string that is generated randomly. This anons will be sent over to this guy here. And this is how the packet frame looks like. This is how the Wi-Fi frame looks like. You can observe here, WPA key nonce, right? Message number 1. And it is 802.1x authentication. So once this anons reaches here, this guy, the supplicant, it will take the PMK, it will take the anons. Similarly, it will also generate the S-nonce. So A-nonce, it stands for access point or authenticator nonce. S-nonce, it stands for supplicant nonce. Again, it's a random string that this guy has generated on random. So S-nonce and A-nonce are with this guy now, right? It already knows its own MAC and the MAC address of the access point. So it will take all of that information and then it will generate PTK. PTK is pairwise transient key. So this is the formula to generate PTK. You take PMK, you take A-nonce, S-nonce, authenticator MAC, supplicant MAC, and you get PTK, right? Now PTK is separate for every user, right? So every client that is connected to your access point is going to use a separate PTK to encrypt its traffic that it is sending to the access point. So after generating the PTK, this guy, the supplicant, will send the message to the authenticator. And in this message, it is going to send the S-nonce that it has generated, right? This is how the packet will look like. So you can observe, this is the nonce part. Message number is 2, right? There is WPA key data and WPA key mic, right? But for now, you can ignore those. So once you have sent this part to this, now this guy also has S-nonce, A-nonce, and MAC of both the devices, right? So it can also generate PTK. So now both parties have PTK. PTK is again 256 bits long, right? After this, the authenticator or the access point will actually generate a GTK. So it is generated when the first client connects to the access point on that network. And for after that, for the consecutive clients, it is kept same. So GTK is the group transient key. You use group transient key to send the to encrypt the messages that are broadcast or multicast in nature, right? So just like you have your ARP packets, right? So ARP packets, when you want to send them, you want to send this to multiple devices, right? So instead of encrypting them with separate keys, you can just use a group key, so that you have to do less encryption for the same packet. So we can use GTK for that. So what the access point is doing here, it is generating the GTK. It is adding the GTK in message 3, and then it is sending this message to the supplicant. And in addition to the GTK, it is also sending MIC again. MIC is nothing, it's also called Michael. It's more of the authentication code, right? So it is to make sure, by checking the MIC, you can actually tell if the other party has a valid key or not. That is how it is used. So GTK is generated by the access point and it is sent to the client. It is not derived like PTK because it is same for all the clients that are connected to a BSSID, right? It will be used for broadcast and multicast, and from time to time it is changed. Whenever a client will leave the network, at that time it will be changed again and it will be sent to the all the clients. So how the GTK is being transferred? It is transferred in your message 3, right? But because again GTK is also sensitive, so you cannot transfer it in plain text. You can use a part of PTK to encrypt it and then you can transmit it. So your PTK, which is 64 bytes long, you can divide it into 5 parts. First part is the key confirmation key, that is KCK. This is the one that is used to compute MIC on the WPA EAPOL message, right? This is the one that is will be used to compute the MIC. Then you have KEK. KEK is the one that is used to encrypt the GTK. Then you have TK. TK, or the temporal key, is the one that will be used to encrypt and decrypt the unicast data packets. And then similarly, you have MIC authentication TX key and MIC authentication RX key, right? So these are to compute MIC on the unicast data packets that are transmitted by access point and station. So one key that we generated PTK will be divided into 5 different keys that will perform other tasks. And this is how it will look, right? This is your message number 3. Again, you can see some nonce here, but important thing is that you are able to see MIC here and the key data, right? And now this packet, uh, it is encrypted, right? So you won't be able to see what is there in the WPA key data, right? However, if you decrypt it, because when you decrypt it, the Wireshark will be able to know the PTK. It will be able to generate the KCK, KEK, and then you will even be able to see the decrypted GTK. There you can see, right? This is your decrypted GTK, and KCK and KEK is also shown. So it is after the decryption. Once you provide it the passphrase, right? After that, it will actually show you like this. And then the message 4 is to acknowledge that key is installed on the supplicant side, right? And once this message reaches the authenticator, the 4-way handshake is completed, and now both parties can use the TK to send the unicast messages, right? So this is the message 4. You can see the MIC, right? Now, what if this supplicant here, right? What if the supplicant or the client, if it is not aware of the right passphrase, what will happen then? So if the client does not know the right passphrase or the right secret passphrase, it won't be able to generate the correct pre-shared key or PMK. If the PMK is wrong, the PTK that it will create or derive will also be wrong, right? And if the PTK is wrong, the part that we use to calculate the MIC, right? Because again, if it is the part of the PTK uh, that we use for MIC authentication, right? So we use it for MIC generation. That will also be wrong. And then in our case, what will happen? Whatever MIC we will calculate and send, it will actually fail the check on the other side. And if that happens, authenticator or access point is going to disconnect this client. That is what happens when you don't have right passphrase. If you have a right passphrase, in that case, you will be allowed to connect. Even if you perform eavesdropping on the four-way handshake, you won't be able to get anything out of it apart from these factors. You will be able to see A nons, S nons, MICs, right? All of this you will be able to see. So if we are able to see A nons, S nons, and MIC, right, what we can do? So this is how the generation of PTK is done, right? You have your passphrase, the human-friendly passphrase or password. You provide it to PBKDF2. It will give us PMK or PSK of 256 bit. And from here, if you take PMK and from the four-way handshake that you have captured as an attacker, right? You have S nons, A nons, AP MAC, and client MAC. So by combining this information and this information, you can actually generate PTK, right? That is how it works. So if we want to perform a dictionary attack on this thing, how we can do this? We can replace this passphrase with a passphrase taken from the dictionary, right? So you have a dictionary, you take one passphrase, you provide this passphrase to PBKDF2, it will give us PMK. This information we have from handshake, right? So you take PMK, you take this information, you get PTK, and then you use a portion of the PTK to verify the MIC that is captured during the four-way handshake. If the MIC matches, it means we have used the correct PTK. That means we have used the correct pre-shared key or PMK, and that also means that we have used the correct passphrase. But if the MIC is not correct, that means we have used the wrong one. In that case, we will take the next one from the dictionary and try it again, right? So this is how the dictionary attack will work. So you will keep trying newer passphrases till the time your PTK is not able to verify the MIC properly. Once it is able to, that means you have correct passphrase with you. So let's understand the packet flow for the WPA PSK. So this is the beacon frame. As you can observe, the SSID name is Wi-Fi WPA, and here you are able to see the channel information, the supported rates, right? And this is the important part, the RSN information element. RSN stands for Robust Security Network, and this information element tells you about the security capability of a WPA network. So here we can observe that the group cipher suite as well as the pairwise cipher suite is AES CCM, which means it's a WPA2 network. If you see TKIP in this place, in that case, it will be a WPA network, right? So by looking at this field, you can actually tell if it is a WPA or a WPA2 network. If it shows you both the AES as well as TKIP, then it means it's a WPA WPA2 PSK network. And how do we know it's a PSK network? From this part here. So if you check the auth key management, you will actually see PSK here, right? So it's a WPA2 PSK network. So this much is clear. Now let's see what all we can do with this information. Right. So if we move it forward, so what we are trying to do now is we are trying to filter out the beacon frames. So we have applied the filter. Similarly, let's also filter out the probe responses. And now we are able to see the control frames. Again, we can also filter these out. We don't really need these. And once all of this garbage is taken out, we are able to see the authentication and association packets and other packets related to the four-way handshake, right? So by now it's very clear to us what authentication and association packets do. Once both of these packets, right, all four of these packets are exchanged, we can then move to the EA poll packets, that is extended authentication protocol over LAN, that is EA poll, right? So this is the EA poll packets. Here you can observe that we can see message 1, 3, and 4, right? But we are not able to see message 2. So it is possible that we might have lost it while capturing it. So it's of no use to us because we are not able to see the complete handshake. What we will do, we will actually look for other complete handshakes, and we can do that by just filtering for EAPOL packets. And there we go. So we can clearly see that these four are not in sequence, right? We have message 2 missing. However, if we check this one, we are able to see packet 1, 2, 3, 4. So that is like the complete handshake, right? So we can use that. So here you can observe, this is the first frame. And in the first frame, you can clearly observe that this was a retransmitted frame because retry flag in the flags is set, right? This was the first one. This is the retry frame. And if we check the body of this frame, we will be able to see this WPA key nonce. We have already seen this in the slides also. So this is the A nonce generated by the access point. Now, if we check the second packet, we will be able to see S nonce or the station nonce or the supplicant nonce, and then MIC is also there. For now, we can just forget about the WPA key data because it only has some information related to the network. The third packet that contains the WPA key data. So this is your encrypted GTK, and then you have MIC and you also have nonce, right? So this is the MIC. Similarly, the fourth packet will also have MIC. Right? So this is how your WPA PSK packet flow looks like. So which packets do we need from the handshake to run the dictionary attack? So what we need is A nonce, S nonce, and obviously the MIC. So either if we have all the four packets or we have packet 1, 2 or 2, 3, we should be able to run our dictionary attack, right? So how we can crack WPA2 PSK? Let's see. Cracking WPA PSK is very easy. We are actually depending on dictionary attacks. Apart from dictionary attacks, there is nothing available. There is no fundamental scheme-based flaw in WPA PSK, just like there is in WEP. So first of all, obviously, we are going to list the Wi-Fi network interfaces that are on the machine. So we have one interface that is WLAN 0. Now we are running aerodump ng on this interface so that we are able to see the network that are in the vicinity. So only one network is operating. The ESSID is protected underscore network, and this is the BSSID. It's operating on channel 4. So what we can do is we can stop the aerodump ng and we can again start it on channel 4 and we can start capturing the traffic, right? So once it is started, we should be able to also observe that there is one client that is connected to this specific network. This is the client. Now, in order to capture the WPA four-way handshake, we need the client to connect to the access point, right, while we are performing the sniffing. But it is already connected, right? So we won't be able to get that. So what we have to do in this case is we have to forcibly disconnect the client from the access point, and when it will connect at that time, we will capture the handshake and then we can run the dictionary attack. So we are using air replay ng to perform the deauthentication attack. -0 stands for deauthentication attack. Then we are defining number of packets that we want to send, 100 in this case. And then we are defining the BSSID. And we want to use WLAN 0 interface. So once we run this command, what will happen is our client will get disconnected and it will try to reconnect to access point. And when it does, our aerodump is going to capture the handshake. And you will be able to see something like this on aerodump ng, right? So once this is done, we can exit the aerodump ng and we can then run aircrack on this PCAP, and we can also pass the dictionary file to the aircrack, right? So once we do this, aircrack will go over the passphrases that are available in the dictionary file, and if it finds a match, it is going to show us, right? So in this manner, we can crack WPA2 PSK and recover the shared passphrase. It is pretty straightforward. Once you do it by your hand, it will become more clearer, right? So this is the dictionary attack, right, that we just discussed about. Now, the most time-consuming part of this flow is this part, the PBKDF2, right? Why? Because if you remember, it is going to do 4096 iterations for every calculation that it does. So it is going to slow us down. So if we want to fix that thing, what we have to do is we have to calculate the PMK in advance. We have to pre-compute the PMKs. Now, thing is, your PMK calculation depends on the SSID as well as the passphrase. So you need to find a lot of common SSIDs, and then you can take a dictionary file and you can pre-compute the PMKs. Once you have the PMKs with you, after that you just need SNONs, ANONs, supplicant MAC, authenticator MAC. These cannot be calculated because these you have to take from the handshake, right? So the only pre-calculation that we can do is for the PMK, right? So you take SSID list and the dictionary of passphrases, and you create a list of PMK. And from this PMK on the runtime, once you have a four-way handshake, you can get all of this information. You can create the PETK and then you can check the MIC. So we can use a tool called GenPMK to generate the list of PMKs. So GenPMK is a very good and very popular tool. You just need to provide it the dictionary file, right? Dash D is to define the output file name, and dash S is to define the SSID. So we are calculating these Gen PMKs. So we are calculating the PMKs for home SSID and for the password list that is provided here. Once it is generated, right? So in similar manner, you can also do the same by using cowpatty. Cowpatty also allows you to perform the dictionary attack with the pre-computing PMK list, right? So you run cowpatty, you define the pre-computed PMK list. This is the one that we have generated in the last step. Then you define the SSID, that is dash S. This is the name of the SSID. And here you then define the capture file. Cowpatty will then use this pre-computed PMK list, and it will try to crack the passphrase for the network. Another way of using it is to first convert this GenPMK list into a SQLite database or SQLite file, I'll say, using aerolib-ng. So once you do this, after that, you can directly use aircrack-ng. You can pass it the SQLite file that contains the PMK list, and you can then pass it the capture file. And it will then use this SQLite file to crack the passphrase. Another way of improving the speed, right? Another way of doing it more faster is to use public cloud-based GPU instances. So for example, your AWS, Amazon AWS services now provides you the GPU instances in EC2 category. So you can install Hashcat on those instances. You can use a cluster of multiple EC2 based machines, right? With the intelligent software that can distribute the key space and dictionaries. And using this, you can crack passphrases pretty fast. However, this approach, right? So it actually violates the TNC of most of the cloud providers. So if you want to do this, please make sure that you go through the TNC first. So once you have the passphrase, you can then connect to WPA WPA2 PSK network by using same WPA supplicant, right? So you can again define the WPA supplicant config file. You have to define the SSID, the key management scheme, the PSK, and by using this command, you can then connect to the network. Now comes the AP-less cracking, AP-less WPA PSK cracking, right? So we have already covered WEP cracking. We learned how to perform cafe latte attack for AP-less WEP cracking. After that, we learned how to perform dictionary attacks on WPA WPA2 PSK networks. And now we are learning how to perform AP-less attacks on WPA WPA2 PSK networks. So you don't have your access point with you, but you want to crack the passphrase for WPA WPA2 PSK network. When there is only a probing client in the vicinity. So what you have to do in this case, first of all, when you have a probing client, you need to give it a honeypot to connect to, right? So this honeypot needs to be of the same SSID that the client is probing for. So here you can observe the first parameter is the interface. The second parameter is the driver that HostAPD is going to use. Then comes the SSID. VSSID is also defined. It is obviously optional, but if you define the VSSID, it looks more real. Uh, when you don't define the BSSID, it actually takes the MAC address of the interface. Then you are defining the passphrase, the key management, that is WPA PSK, RSN pairwise, that is TKIP in this case, which means this configuration is for WPA PSK. And then you are defining the channel. And by using hostapd, you can easily host this specific honeypot. Instead of using TKIP, if we use CCMP, then it will mean that we are hosting a WPA2 PSK network. We can also define something like this, which means it will be WPA and WPA2 PSK network, right? So let's remove it for now. So once you have created the honeypot, after that, you can wait for the client to connect to it. When the client tries to connect, you can at that time capture the four-way handshake, and then you can perform the dictionary attack on it. And once you perform the dictionary attack, if you have the right passphrase in the dictionary, you will be able to recover the passphrase for the network. It is very simple actually. So, and this is anyway something that you are going to do in your homework class. But yeah, let's actually go over this once. So this is the lab. So once you're inside the lab, here, and this is just the architecture of the lab that we are seeing, checking, right? Not really relevant here. So if we list the devices, the Wi-Fi interfaces that are available on this lab, we can clearly see that WLAN 0 and WLAN 1 are available here. Then we are running AeroDump on this interface, and what we are seeing here is a probing client. So this probing client is looking for this specific SSID, right? There is no network in the vicinity. So what we are going to do now is we are going to fix our AeroDump on channel 6, and we are also saving the capture file. So now if you check the listing by opening another tab, you'll actually see that WLAN 0 is fixed at channel 6 and it is in monitor mode. So what we are going to do next here is we are going to create a hostapd conf. So I'm just pasting the hostapd conf that we have seen on the slides. The only difference here is I'm changing the SSID, right? I'm changing SSID to woodwork_LLP because that is the network that our roaming probing client is actually looking for. WPA passphrase is not known to us, but we can use any password that we want to in this case. Just put any dummy password here. Doesn't really matter. So save this and run it with hostapd. When we run this with hostapd, the network will be ready and the client that is probing, right, will try to connect to it. And you will actually see this message that says AP station possible PSK mismatch. This is because our honeypot, right, we don't really know what's the right password. So we have just mentioned any arbitrary passphrase that we that we want to. So that's why this is mismatching, right? We don't know the real passphrase that is known to the roaming client, that is saved on the roaming client. So what we will do now, we will stop it. But the main thing that we wanted to do, we wanted to capture the partial four-way handshake. And as you can observe in AeroDump, we were able to do that. So we can now stop AeroDump ng. And because we have captured all the traffic for this network in capture-01.cap, we can actually use aircrack. We can pass it the dictionary file, and we can then run it on this specific capture. And then it will let us know that if the passphrase, right, if the correct passphrase is present in the dictionary file, it is going to show us that file, that passphrase, that is Cassandra. And now we can copy this Cassandra passphrase and that is the right passphrase for us. So if we just replace this passphrase here in the configuration, and if we create this honeypot again, this time you will see that the client will actually connect to this, right? So instead of seeing a possible mismatch message, we can see that AP station connected, right? So this means we have found the right passphrase by attacking this client using our AP-less attacks, right? So it is that simple. Just like WEP, we can also decrypt the WPA2 PSK traffic using Wireshark. Again, you have to go to Edit, Preferences, Protocols, IEEE 802.11, and then it will give you this option. Just make sure that the Enable Decryption checkbox is checked and add your entries in this field here, right? So I will leave this part to you so that you can figure out what to exactly put here in case of WPA WPA2 PSK and how to put it to decrypt the traffic. Similarly, if you want to do this on CLI, you have ARD-CAP NG. Just like we were able to pass uh, dash W and the key for the WEP network, we can actually use dash P and we can pass the passphrase to decrypt the traffic for WPA to PSK. So with that, our planned syllabus for today is completed. The lab assignments are these labs. So, try to do these labs, try to do these on your own before, so without taking a look at manual, first try on your own. If you're not able to do it, then only, please take a look at the manual. From what we have covered today, you should be able to do these on your own. And then this is the assignment to make you think. Please try to find out what are the weak IVs and how they leak information regarding the WEP key. That's the first question. Second question is how to crack a WEP encryption if you don't have enough packets. Third is why WEP is using 40-bit and 104-bit key and 24-bit IV, but not 64 or 128-bit static WEP key, right? That's the third question. Fourth question is, learn to decrypt WPA2 PSK traffic with Wireshark and ARD-CAP NG. And the final question here is, you have captured four-way handshake for WPA2 PSK network, but you were not able to get a beacon frame of that network. Again, it's a hypothetical situation. The secret passphrase is present in the given dictionary file. Will the WPA2 PSK cracking using AirCrack NG work? If it will work, how to do this, right? That's the assignment. That's the thing that you have to figure out. Again, if you're not able to do this, don't worry. We are anyway going to discuss these in the beginning of next session. So now if you have any questions, please ask those. Okay, can you go back a slide, please? Don't worry, Mike, I'm anyway going to share all the slides with you, right? So do you want me to go here? The lab assignments? Okay, that's good that you like it. Any questions, guys? Any doubts, any questions that you might have from this session or from the previous session? Okay, that's good. That's good to hear. So guys, if you don't have any questions right now, that's totally fine. You guys can try these labs. So I have mentioned the links here. These labs will cover the personal aspect of the Wi-Fi network security, right? So you go through these, try to perform these attacks on your own. I'll also say, please also try the Wi-Fi badges that we have on Attack Defense. So when you have solutions available to you, you don't understand how difficult it is, right? So it is good after doing these labs, try your hands on some of the basic and intermediate Wi-Fi challenges on the verifiable badges section. So in the verifiable badges section, we don't actually provide you solutions. We don't actually give you hints. So that is where you will actually, see how easy or how difficult it is, right? So I'll recommend that. So with that, guys, our session 2 is concluded. If you have any questions at any given time, please let me know. I will post this recording within 12 hours of this session ending, and the slides will be posted right away along with the demo videos. So you guys can go through it and let me know if you have any questions. So thank you for attending the session 2, and I'll see you in the next class. Bye bye.